thank Jianfeng for the introductions, and I want to thank the organizer for organizing this wonderful workshop. In this talk, I want to share some new insights about the system bus interaction models to prepare the quantum ground state and the thermal state. Basically, in this talk, I will propose one simple quantum ground and a thermal state preparation algorithm based on the system bus interaction model, and I will also share some very recent insights in this model. So in this talk, I will mainly cover the results in these two papers. So the first papers is our collaboration work with the Yongtao Zhang from Caltech, Professor Lin Ding from UC Berkeley, Professor John Presco from Caltech, and the second work is our collaborations with Dr. Ke Wang. Ke is James Van Lu postdoc in University of Michigan. Okay, so basically in this talk, we will still consider how to prepare the quantum ground state and the thermal state, and we will propose algorithm for it. The intuition is still to use the open quantum system. Basically, here we can view the open quantum systems as we have the system part, and we coupled with the bus density operator. Then we do the evolutions for certain time t. We trace out the bus to get one update for our system. It basically involves the interactions with the bus and the trace out process. So the intuition to do this is the open quantum system in nature always thermalized fast. Now, if we want to build an algorithm based on this framework, basically what we want to do is we want to design some algorithm that working as a fridge. So in fact, this is my fridge when I was a postdoc in Berkeley. Okay. Yeah. Okay. Good. So then in the last few years, there are a lot of work to achieve this, and the initial ideas is to use the Lindblad dynamics. Here, we can imagine that we have the reasons we want to use the Lindblad dynamics is it's a very good mathematical model to approximate the open quantum system. Basically, we have the system bus interaction, and if we assume that we have the weak coupling between system and the bus, and after the Bohr-Marr curve and also circular approximation, we can show that the evolution of the system density operator can be approximated by this Lindblad dynamics. Okay, this is the intuition. Then it's true that in the real physical world, there's a more Marr curve circular approximations might not be true, meaning that the Lindblad dynamics might not be a good mathematical approximations to a physical system. However, here we are still, we are just designing some algorithm. Even this approximations is not true, we can still see it as an algorithm tool to prepare the ground state and the thermal state. The main advantage is we can have provable guarantee. So these ideas was initially proposed by Chen, Castellano, Brandau, Gillian in 2023. It turns out that this is a very promising direction. So in fact, in the last few years, I think people in this room have made tremendous progress towards proving the end-to-end complexities for the Lindblad dynamics-based algorithm. Basically, now we have relatively good understanding to the correct fixed point, the efficiency and the efficient simulations of the Lindblad dynamics algorithm, and also for certain physical models, we can prove rigorous mixing time guarantee. Then combining this three perspective, we can finally show the end-to-end complexity guarantee for the Lindblad dynamics-based algorithm. Okay. So then to motivate our work, we can quickly look at how we simulate the Lindblad dynamics algorithm. Essentially, when I have a Lindblad dynamics. On the quantum computer, the simulations essentially involves 2 steps. First, we need to block encoding the coherent part and the jump operator. The jump operators often involves the linear combinations of Heisenberg evolution. Okay, so I think I have a typo here. Okay, then after we construct this block encoding, we can use the well-developed Lindblad simulation techniques to simulate this dynamics up to the mixing time. And the query complexity often scales linearly in capital T and polylog 1 over epsilon. This is very good. Okay, so however, one bottleneck to make this algorithm early fault tolerant friendly is the block encodings of these jump operators is not that easy. So basically, here are 2 examples where we can construct the block encodings of the jump operator. And this quantum circuit often involves the linear combinations of unitaries or multi-control backward Hamiltonian simulations or quantum Fourier transform. So all of these operations are not that friendly to the near-term quantum computer. Then a natural question to ask is it possible for us to make this simpler? Okay, basically, under the open quantum system framework, we want to ask the following 2 questions. First, can we find a simpler algorithm that is more suitable for near-term devices? And also, we want to preserve rigorous guarantees. Okay, here, this rigorous guarantee is very important. And the second question is, does a provable correct algorithm have to belong to the Lindblad dynamics regime? Meaning that we assume very weak system-bus interaction. Okay, so in our 2 papers, we give positive answers to these 2 questions. So basically, in the first paper, we propose a simpler algorithm to prepare the ground state and the thermal state. And this algorithm is more suitable for the near-term device, and it can also preserve rigorous guarantee. And for the second the questions, we rigorously show that the ground state and the thermal state preparation algorithms can go beyond the Lindblad dynamics regime, meaning that we no longer require no longer require very weak system bus coupling. Okay, so basically, the main ideas of our algorithm is now instead of going to the Lindblad dynamics regime, we directly see the system bus interaction models as an algorithm tool to construct our algorithm. Basically, we want to answer the following question: how to set up the interaction system so that it can prepare the ground state and the thermal state. And to show the end-to-end complexity, we also need to discuss the simulation cost and the convergence rate of our algorithm. Okay. Now I want to first introduce our algorithm. In the beginning, I will still consider the weak system bus interaction regime. Okay. This is the outline of our algorithm. Basically, this algorithm involves system bus interactions in each step. So in each step of my algorithm, I will couple my system density operators with a bus density operator. Then I will do a total Hamiltonian simulations for certain time capital T. We trace out the bus to get one update from rho n to rho n plus 1. Okay? So here in our total Hamiltonian simulation, in our papers, we use a time-dependent Hamiltonian. And the bus Hamiltonians is just a single ancillary bus, poly C here. Okay? And in each step of our algorithms, we will initialize our bus density operators as the thermal state with respect to the bus Hamiltonian. Okay? Here, the first advantage is in our algorithm, we only need to use a single ancillary bus. Okay? And furthermore, for the coupling between the system and the bus, this AS is our three coupling operators we can choose. And in most of the cases, we will choose AS to be local coupling operator. This basically means the interactions between the system and the bus are local operators. Okay? So then, if you look at the time-dependent Hamiltonians, it only involves the original system Hamiltonians plus some local terms in between the system and the bus. This basically means the simulation of this total Hamiltonians is almost as hard as the simulations of the original system Hamiltonian. Okay? There is almost no extra difficulty. Okay? Then in each step of our algorithms, what we do is we couple the system density operators with the thermal bus density operators and simulate this the time-dependent Hamiltonian for certain time capital T. We get rid of the bus and reset it. This is one step of our algorithm. We run these quantum channels for enough numbers of times to ensure that it can converge. Okay.
So this is omega in the bottom line?
Yeah, so this omega is a parameter we need to choose. I will talk about how to choose this omega later and also tell you the physical intuitions about how to choose it. Okay.
So why can we assume we can start the bus state with this thermal state? Because the goal is prepare a thermal state, but we start with the thermal state.
Yes, that's a very good question. So here the key is I only initialize my bus as a thermal state with respect to the bus Hamiltonian. And this bus Hamiltonian is just a single policy. So it's just a mixed state between 0 and 1, which is very easy to prepare. Okay.
So you have multiple coupling operators or one?
Can you use it along?
You have multiple coupling operators.
Yeah, good. So in each step of my algorithms, I will only use a fixed coupling operator, but I can choose this coupling operator randomly. So in my next slides, I will also give some examples about how to choose this coupling operator.
The support is fixed or not?
What?
The support of the coupling operator is fixed or not?
It's not fixed. Yeah, it's not fixed. Okay. Any other question? Okay. So now I will give more detailed the introductions to this algorithm framework. So basically, in each step of my algorithms, I will initialize my bus as a thermal state. And here I will choose the coupling function ft as a Gaussian interaction function. Okay, so in fact, this choice is inspired by the paper's ZKBG. Okay, so however, in practice, if we really want to get rid of the time dependency here, we can also choose it to be a constant interaction function. This will also work. Okay. And about the choice of omega. So in practice, we need to choose omega randomly. Here we can so we can choose omega uniformly from some interval, but I want to emphasize this distributions is flexible. You can design it in your own algorithms. And the physical intuitions of omega is in each step of my algorithms, omega approximates the allowed energy transitions in each step. Okay, basically, it describes the energy difference created by your jump. Okay, and the matrix AS basically corresponding to the coupling corresponding to the coupling operators in the Lindblad dynamics framework. And here in each step of my algorithms, we should also choose AS uniformly from a proper set. For examples, if we are in spin system, then we can choose AS as a single Pauli set. And if we are in fermionic system, we can choose AS from single creation annihilation operator set. Okay. Any question?
So in principle, could it be fixed, or does it have to be always chosen randomly?
Good. So this is a good question. In principle, it can be fixed for certain Hamiltonians. So I think the simplest way you can imagine this is in the Lindblad dynamics framework. It's possible that you only have one jump operator. Then this means this AS is fixed. Okay.
So here you said single qubit path, but would you consider like slightly bigger path, and would that change a lot of things? Or?
Yeah. So in fact, I do think even you add the extra ancillary qubits, the results are still the same. Yeah. So all would be similar. Yeah. To my best knowledge.
Because like usually people would say that, oh, I need a big path. You know, that's what physicists would say.
Right. So that's a very good question. So in fact, so if we want to add a lot of bus, then we can actually do the repeated interaction framework, meaning that we can remove the trace out, and we only do the trace out in the very end. Yeah. So if we are allowed to add a very huge bus. Yeah. Okay. Good. Okay. Okay. So next, I want to quickly talk about the simulations. So as I mentioned before, since my Hamiltonians is just the system Hamiltonians plus some local terms, the simulations will be very simple. And in our papers, we basically consider the second order Chorter formula to do the Hamiltonian simulations. The main advantage is in the second order Chorter formula, it only involves the forward Hamiltonian evolutions, which is friendly to the digital device. And if we do the second order Chorter formula, then the complexity for each step of our algorithms will be t to the power 3 over 2 over square root of epsilon. And the advantage of this algorithm is single ancilla, no need to construct jump operator, and also only involve forward Hamiltonian simulation. Okay? So then if we want to talk about the end-to-end complexity, we also need to consider how fast my quantum channel mix. So basically, the end-to-end complexity will be single-step complexity times tau mix. And here, since we have a discrete quantum channel, when I talk about the mixing time, we need to define it to be the integer mixing time. Basically, how many times I need to apply my quantum channel so that the resulting state is close to the fixed point. Okay? This will be the end-to-end complexity. Now, we look at some theoretical guarantees. In our first papers, in the first main result, we can show that the fixed point is rigorously closer to the thermal state and the ground state. Basically, for both thermal state and the ground state, we can prove the corresponding bound. So if this is your first time looking at this bound, so you can basically understand it as if I want to make this distance to be very small, then I need to choose sigma to be very large and alpha to be very small. Okay. However, here there are some very important technical questions I need to answer. Because in our algorithms, when I design my algorithm, this my quantum channel will depend on alpha and sigma. This basically means the mixing time of my quantum channel will depend on alpha and sigma. Then in the worst case, it might happen that if I choose my sigma to be very large and alpha to be very small, then my mixing time will blow up. Okay? If this happens, then this bound will be meaningless. Right? Okay? So luckily, in our papers, we can show that when I choose alpha to be very small, it shows that this tau mix will blow up. However, this alpha square times the tau mix will stay as a constant. This is the reasons in this bound. I basically pick out this factor here. Okay, so then if and furthermore, this constant is independent of sigma. Okay, now if we assume this is true, then basically to achieve epsilon precision here, I only need to choose sigma to be sufficiently large and alpha times the square root of sigma to be sufficiently small. Okay, this means under these assumptions, we can achieve arbitrary high accuracy under this framework.
If sigma and tau are chosen, or sigma and t are chosen like at similar size, should the time evolution be like a time-ordered exponential, or do you evaluate it at a point in time?
No.
It's a time-dependent Hamiltonian, right?
Yes.
And it varies at the same scale on which you want to simulate it?
It varies as no. So in fact, so it's true that this is a time-dependent Hamiltonian, and the only time-dependent part is this function ft here, and this function ft is basically a Gaussian decaying function. So you can imagine that I run this time evolutions for enough long time, then we don't see this interaction function anymore.
Right, but shouldn't it then be like a time-ordered exponential of this?
Time-ordered exponential of the right. So mathematically yes, but in the simulations you just need to do the Chord formula. Yeah, so
okay.
there is a Chord formula for the time-dependent Hamiltonian, right?
Okay.
Yeah. Mm-hmm. Okay. And also, I want to emphasize that if you really want to get rid of the time dependency, you can also run it with a constant interaction. So this can also work. Mm-hmm. Good. Okay. So
I think there is another aspect to this question, which is MEM shift.
MEM shift.
Right. The Trotter simulation is one thing, but the difference between time ordered and on-time ordered.
Is a difference.
Not sure whether it is which one.
No. I was just wondering if you have like control over the difference between the time ordered and non-time ordered. Like if you say you do the Trotter formula, I imagine that you just do Trotter steps where you evaluate this Hamiltonian at a single point at each.
Yeah. So that's what we do. That's what we do. Yeah. Mm-hmm.
But you have control over like the difference between doing that and doing a time-ordered exponential then, because the Trotter step is much smaller than t, I guess.
Yes. I think that's correct. Yes, I think that's correct. Yeah. Okay. Yeah. So thank you for the comments. Okay. So we go back to the talk. So as I mentioned, if we assume that alpha square times the tau mix is a constant, then under this framework we can achieve arbitrary high accuracy. Okay. Then our next result is for a class of physical Hamiltonians, we can rigorously prove that this rescaled mixing sin time t mix defined as alpha square time tau mix is a constant when I choose sigma to be sufficiently large. Basically, this rescaled mixing time will scale polynomially in the number of qubits. Okay, so here, in fact, while we consider the rescaled mixing time, this is a very intuitive. So in our paper, the high-level proof idea is when I choose my alpha to be sufficiently large, I enter the weak interaction regime. Then basically, my quantum channel can be approximated by a Lindblad dynamics. And we all know that the Lindblad dynamics has a certain mixing time. And this mixing time induces this rescaled mixing time here. Okay? And here, I want to note that to make this analysis true, I need to choose alpha times the square root of sigma to be order epsilon. Okay, and so I want to emphasize this rescaled mixing time is independent of sigma and alpha. Now we can put everything together. So basically, for this system bus interaction framework, we can have the following end-to-end complexity. After I adjust my parameter properly, this total Hamiltonian simulation time will be polynomially so in the number of qubits and also 1 over epsilon. Okay, so any question up to now?
So because of, as you're saying, you have to pick alpha kind of small, and this means that the number of steps will necessarily scale polynomially with epsilon, right?
Yes, exactly.
So you think that this is sort of tight or necessary, or do you think that?
Right, so that's a very good question. So in fact, in the third part of my talk, I will tell you it's not tight. Okay.
So here the ground state limit is literally just the beta goes to infinity limit. So all you have to do when you are actually building the algorithm is to reset the ancilla always to the ground state, or how do you do it?
No, so in fact, if you consider the beta go to plus infinity t limit, then this complexity will blow up.
Okay.
The key is here we have a special gap. So this basically means you don't really need the to let beta go to infinity. So there is some threshold like you can stop because you have the special gap. But if you don't have the special gap, then you can imagine it will be super hard.
Right. So basically, in practice, you would take a very large beta.
Yeah.
Okay.
Any other question?
So your quantum channel, is there any symmetry property with respect to its fixed points?
Any symmetry property? What do you mean?
Like detail balance.
Yeah, so in the weak interaction regime, yes, we can show approximately detail balance, but not exactly. Okay, good. Okay, so now I can talk about the third part, which is beyond the Lindblad dynamics. So here we recall that in our algorithms, we do the system bus interactions. And why I call it weak interaction regimes? Basically, because if we consider the cumulative interaction strength of a single step, then it equals to alpha times the square root of sigma. And to make sure we converge to the Lindblad dynamics, I need to make this number to be very, very small. Okay? So basically, my quantum channel can be approximated by a Lindblad dynamics. And in our recent papers, we rigorously show that we don't need this condition. So in fact, in our papers, we show that as long as alpha times the square root of sigma is a constant, the thermal state and the ground state can still be preserved by our quantum channel. So a simple way to understand this is in our theoretical result, we can get rid of this term. Okay, so in the theoretical result, the arrow will basically depend on beta over sigma times alpha square times tau mix. Okay, so then in our new result, one advantage is if I can choose this alpha to be larger, it can help us reduce the computational cost of my algorithm. Previously, I emphasized that for this kind of algorithm, this alpha square times tau mix called the rescaled mixing time often stays as a constant. This means that the number of repetitions of my algorithm scales as 1 over alpha square. And now, since I can have a better bound for alpha, I can improve my computational cost by a factor 1 over epsilon square. Okay, and more importantly, our result shows that this open quantum system-based state preparation algorithm can theoretically go beyond the Lindblad dynamics regimes, meaning that if we use the system bus interaction models to prepare the ground state and the thermal state, we don't necessarily require weak interactions between system and the bus. We can kind of go beyond that regime to achieve for like early fault tolerant friendly and more efficiency. Okay. Good. So finally, I want to show some numerical results. So this is a very small model, 1D TFIM model with 4 qubits. And on the left-hand side, you can see that when I increase my alpha, this my quantum channel will mix much faster. And even I bring alpha times the square root of sigma equals to order 1, I can still achieve very high accuracy here. Okay? And on the right-hand side, you can get 2 information. First, you can see that in my algorithm, even I increase sigma, the spectral gap of my algorithms always stays as a constant. Okay? So this basically means the tau mix of my algorithms always stays as a constant with respect to sigma. Okay? And also, if I try to match this tau mix with respect to different alpha, it's almost so the rescaled mixing in same times almost stays as a constant, meaning that tau mix stays as 1 over alpha square. Okay? Here, the largest alpha, I can bring, I think, it to equal to 1 or 2 here. Okay? So this is for the thermal state preparation. And for the ground state preparations, we can also see a very similar phenomenon. So the phenomena are basically the same. Okay? And we also try the 4 qubits Hubbard model. So basically, we still see the exact phenomenon as before. Okay?
Sorry, one question. Is this fidelity with respect to the Gibbs state or the fixed point of that channel with those parameters?
Good. So this is with respect to the Gibbs state. Yeah.
Okay, so it's
very good question.
But then isn't it very surprising that even for alpha times square root of sigma equals say 1, you still have fidelity essentially
1. Yeah. So that's what we can prove in our paper. So even I allow alpha times the square root of sigma equals to order 1, as long as I choose my sigma to be sufficiently large, I can still have correct fixed point. Okay, good.
So what's the T and the U in this example?
What was T and U?
How large is on-site and?
Yeah. So I think I don't remember, but I just use some common choice. So in fact, the choice of the parameters is the same as I think which paper? Yeah, I forget. Yeah.
It's related to that. So are these results independent of which phase of the model you're in?
No. It's actually independent of which phase of the models you are in. So later I will show you the ANNI model, which might be more interesting.
Okay. So it doesn't matter if you're paramagnetic, ferromagnetic, whatever. Yeah. Okay.
Does not really matter. Yeah. Okay. Good. So next, I want to show you something that we don't have very good understanding, but might be very interesting. So in our papers, we can show that once this alpha times the square root of sigma stays as order 1, we can prove the correct fixed point. However, we recall that in our total Hamiltonian, the coupling strength stays as alpha over square root of 4 sigma. This means when I choose sigma to be very large, this alpha over square root of sigma is still very small. Okay? We still need a very, very small coupling between system and bus. In our numerics, what we can see is even I bring this alpha over square root of sigma to be order 1, I can still have correct fixed point. Okay? This kind of meaning that even I allow this coupling strength to be order 1, the algorithms will still converge to the correct fixed point as long as I choose sigma to be very large. Okay? This is only numerical result, and we don't have theoretical understanding to it. Okay? So we also test these models for this ANNI model. So the reasons we are interested to this is in one of the previous papers, we can show that these algorithms, so for this model, the adiabatic evolutions will fail. Okay. However, for this dissipative dynamics based algorithm, it will still converge to the to the correct ground state energy. And here we can allow this alpha over square root of sigma equals to 1. Okay? We can even test this phenomenon for larger system. Here I try the free fermion model. The reasons we try it is for the free fermion model. It's exactly solvable. So we can go to very large system size. And the gap scaling will basically be 1 over n. And more importantly, you can see that even in a larger system size, the relationship between tau mix and alpha square still holds. So we still have the rescaled the mixing time stays as a constant. And here I can bring this alpha over square root of sigma around 0.5. Okay, so for the spin models, we have also tried the 12-qubit system, and again, I chose alpha over square root of sigma equals to around 0.5. And the exact simulation showing that for so at least for the ground state preparation, they can always converge to the ground state. Okay. Okay. So finally, I want to introduce some open question here. So as you can see in my talk, I think our two work really only take one step towards designing the system bus interaction algorithm to prepare the ground state and the thermal state. There are a lot of open problems to be done in these directions. For examples, how to prove the mixing time for more alphas with more complicated models, and a more difficult one will be how to prove the mixing time for the large alpha and rigorously justify this relationship. Here, the main difficulty is in the system bus interaction model, we will always have some extra lamp shift term, and we don't exactly satisfy the detailed balance condition. And this is exactly the reasons why we need to choose sigma to be very large. Okay, these conditions, so it's a very in fact very similar to this CKBG paper. And one interesting to ask is it possible to achieve exactly detailed balance condition? So if we can do this, then possibly we can improve this sigma to sigma equals to order 1 or even log 1 over epsilon. Okay. Then another question is how to do the large-scale simulations for this system bus interaction framework. Here we have tried some tensor network techniques to do it, but there are still a lot of things to be done. Okay, so that's all my talk, and thank you.